Good morning, children. Today we will discuss about line shape function and full width at half maximum for natural broadening, collision broadening, Doppler broadening. Let us go with the presentation. Okay, we will discuss about line shape function and full width at half maximum for natural, collision and Doppler broadenings. Full width at half maximum can also, we can say FWHM. And here line shape function, we have to calculate the line shape function and also the full width at half maximum for these three broadenings. So here line shape function, or we can say it as line broadening, which has a great importance, which determines the operational characteristics of the laser, Now we will discuss about Doppler broadening. So Doppler broadening can be obtained from the Doppler effect. So already we have an idea. If we consider any gas, the atoms which are present in the gas, they undergo the random motions. Suppose if we consider the stationary atom, we have a particular frequency for that stationary atom. But whenever the atom which undergoes the motion, what will happen when it interacts with the radiation? Then apparent frequency of the incident wave is different from the frequency seen from the stationary atom. So this is nothing but Doppler effect. That means if we consider the frequency of the stationary atom, we can observe a change which the atom undergoes the random motion when it interacts with the radiation. The apparent frequency of the incident wave is different when we compare with the stationary atom's frequency. This is nothing but Doppler effect. So Doppler broadening can be obtained from the Doppler effect, and Doppler broadening is the broadening of spectral lines because of the Doppler effect. That means we can observe velocity of the distribution of atoms or molecules are different. So emitting particles also result in different Doppler shift. So this effect, which is nothing but line broadening. So equivalently, resonance frequency of the atom shifted due to the motion. So thus if we represent the frequency of the instant wave, then atom moving with the velocity whose component is in the direction of radiation is Vz. That means here the atom which is moving with the velocity and its component is in the direction of radiation Vz. So the frequency equation can be written as omega, which is equals to omega of 1 minus Vz by c. If the incident radiation may interact strongly with the atom, its frequency must be written as. That means if the incident radiation, we can observe a strong interaction with this atom, frequency, how the frequency varies. Frequency equals to omega 21 1 minus Vz by c whole power minus 1. So here omega is nothing but frequency of incident wave, Vz is velocity in a particular direction, z, c is the speed of light, omega 21 is nothing but transition frequency. So thus the effect of the motion is to change the resonance frequency of the atom. So effect of motion, why the atom is moving, because it is the effect of the motion is to change the resonance frequency of the atom. So in order to calculate the line shape function, we know that probability that in an atom has a z component of velocity lying between Vz and Vz plus dVz, which is given by the Maxwell distribution. PVz dVz is equals to m by 2 pi kBt whole power 1 by 2 exponential minus mVz square by 2 pi kBt into dVz. So here m is mass of the atom, T is temperature of the gas, Kb is constant, Boltzmann constant, P is the probability that an atom has a Z component. So the probability of G omega d omega, that the transition frequency lies between omega and omega plus d omega. So here G of omega d omega, here the transition frequency, if it lies between omega and omega plus d omega, the probability of this, which is equal to the probability that the z component of velocity of the atom lies between Vz and Vz plus dVz. So here what is g omega d omega? Change in frequency distribution. G omega is frequency distribution. G omega d omega is change in the frequency distribution. So Vz, which is equals to omega minus omega 21 by omega 21 into C. G omega d omega frequency distribution, which is equals to C by omega 21 m by 2 pi kBt whole power 1 by 2 exponential minus mc square by 2 kBt omega minus omega 21 whole square by omega 21 into d omega. Here this equation corresponds to the Gaussian distribution maximum at omega equals to omega 21. Now let us see the Lorentzian and Gaussian line shapes corresponding to the same width at half maximum. And Gaussian has a larger peak value for a given half width and also much shape compared with the Lorentzian. So here this is the graphical or pictorial representation. Here we can observe Gaussian and here this is the Lorentzian line shapes. So these are the two line shapes. Here Gaussian line shape, which is normal distribution, which is a bell-shaped curve. This is a bell-shaped curve, occurs naturally in many distributions. So we can observe Gaussian distribution or Gaussian curve, and we can see in many distributions. Normally we can observe this one, and this is the Lorentzian distribution. This is the full width at half maximum. So here for each system, half width of the shape function varies with temperature, pressure, and phase or concentration. So whenever we can observe any change in temperature, pressure or phase or concentration, we can observe these full width half maximum can be changed, shifted. So here the distribution is given by the above equation is maximum at omega equals to omega 21. So hence a maximum value of omega 21 equals to 2 by pi whole power 1 by 2 log 2 whole power 1 by 2 by delta omega. So delta omega is nothing but full width at half maximum, which is given by delta omega is equals to 2 omega 21. Here omega 21 is this transition frequency into 2 pi kBt log 2 mc square whole power 1 by 2. And thus in terms of delta omega, Gaussian line shape function can be written as, here in terms of delta omega means delta omega is nothing but full width at half maximum. So in terms of full width at half maximum, Gaussian line shape function can be written as g of omega equals to 2 by delta omega. Here delta omega is nothing but full width at half maximum log 2 by pi whole power 1 by 2 exponential minus 4 log 2 omega minus omega 2 by delta omega whole power 2. So even in the absence of collision and the thermal motion, one has the inherent line width because of finite lifetime of the excited state due to spontaneous emission can be assumed to be of the form E equals to E naught exponential minus t by 2 tsp into e power minus I omega naught t. So here tsp is nothing but spontaneous emission lifetime. Then in the absence of collisions and thermal motions, here one has the inherent line width because of the finite lifetime. Even though if we cannot observe any collisions or the thermal motions, so we have a particular line width because of finite lifetime. For every atom, we have a particular lifetime, and also which is present in the excited state due to the spontaneous emission can be assumed in the form of this is the regarding equation. Now let us see the natural broadening. So naturally we will obtain this broadening. The subfrequency spectrum corresponding to the electric field is given by E average omega, which is equals to integration 0 to infinity E naught e power minus I omega t e power minus t by tsp e power I omega t dt. So E average of omega, which is equals to E naught 1 by minus I omega minus omega naught plus half tsp. So this is the line shape function. So here E naught is nothing but amplitude of the wave, and E bar here it is E average. So thus the frequency spectrum of intensity distribution will be given by intensity distribution I omega proportional to the mod average E omega whole square, which is equals to E naught square by omega minus omega naught whole square plus half tsp whole square. So here tsp is nothing but spontaneous emission time. tsp is nothing but spontaneous emission time. The Lorentzian with a spectral distribution is given by g of omega equals to 2 tsp by pi 1 by 1 plus 4 omega naught omega whole square by 2 tsp. G omega is equals to 2 by pi delta omega naught 1 by 1 plus omega naught minus omega by half delta omega naught whole square. In the above equation, full width at half maximum is given by delta omega naught. So this is the full width at half maximum, which is equals to 1 by TSP. The kind of broadening is known as natural broadening. Now let us see the collision broadening. So collision broadening can be obtained due to the collisions of atoms. Collisions of atom. So if we consider in a collection of atoms in the gaseous form, random collisions occur and thus an atom then interacting with the electromagnetic field, we can see a field which changes its phase abruptly at each collision. That means here whenever we can observe in a gas, the atoms will undergo into the collisions. So whenever it undergoes into collisions, then when interacting with the electromagnetic field, we can observe a change its phase abruptly. A sudden change in the phase can be obtained at each collision. So average time between two collisions is tau. So then the atom no longer sees a monochromatic wave, but instead a wave like that shown in the figure. We cannot see a wave in monochromatic. So here we can observe an abrupt change at each collision here. Phase can be changed. So the field makes random changes in the phase in every collision. For every collision we can observe a phase change here. So line shape function could be given by the power spectrum of E of t is equals to E naught exponential minus I omega naught t plus I phi. Here phi is phase constant. So here t lies between t naught plus tau into t naught, and from distance from here to here it is similar to tau. So t naught is initial time, t is final time, and here phi is phase constant. T lies between t naught plus tau, t naught. So each collision we can observe a phase change of phi randomly. Thus frequency spread of such a wave would be obtained by carrying out a Fourier transform. So E omega equals to 1 by 2 pi integration T naught to T naught plus tau E naught e power minus I omega naught T plus I phi e power I omega T into dt. So E omega is equals to 1 by 2 pi E naught exponential I into omega minus omega naught T naught plus I phi exponential I omega minus omega naught whole power 1 by 2 by omega minus omega naught whole square. So frequency distribution of intensity would be given as intensity I represents with I. I of omega is proportional to mod E omega whole square, which is equals to E naught by pi whole square into sine square omega minus omega naught tau by 2 by omega minus omega naught whole square. Here g of omega represents the frequency distribution of the radiation causing the transition. Then g of omega is, which is proportional to integration 0 to infinity sine square omega minus omega naught tau by 2 by omega minus omega naught whole square e power minus tau by tau naught into 1 by tau naught d tau. G of omega, which is equals to tau naught by pi 1 by 1 plus omega naught minus omega whole square tau naught square, where constant factor integration g of omega d of omega, which is equals to 1. Here constant factor integration g of omega d omega, which is equals to 1, which is known as Lorentzian plotted in figure. So the peak of g omega lies at omega equals to omega naught and has a value of tau naught by pi. Full width at half maximum is given by delta omega equals to 2 by tau naught. So g of omega is nothing but frequency distribution of the radiation. So this is about the full width at half maximum for this collision broadening, and line shape function also we have observed. Let us stop it here. Thank you, children.